In this video, I introduce a stochastic backpropagation of discrete random variables. For a stochastic node X in a neural network, X is first sampled from the conditional distribution P phi X, and then a deterministic function f theta is evaluated at X. For a noisy objective f theta, the goal is to maximize the expectation L with respect to theta and phi, as shown here. This f theta, this p phi, and this stochastic node x. The gradient of L with respect to theta has the form as shown here, which can be estimated by using Monte Carlo sampling, as shown here, where x as sampled from p phi x. Computing gradient of L with respect to phi is a challenge, since this gradient with respect to phi cannot be handled by using Monte Carlo sampling. Two algorithms can be applied to compute the gradient with respect to phi, namely square function estimator and a reparameterization trick. Square function estimator is based on the following entity as shown here, which allow us to rewrite this gradient as expectation form as shown here. This expectation is estimated by using Monte Carlo sampling as shown here, which requires this gradient is differentiable with respect to phi. However, alpha theta is not required to be differentiable or even continuous as a function of x. Therefore, the square function estimator can be used for both discrete and continuous random variables. The estimator based on Monte Carlo sampling is unbiased but has a large variance. In variational autoencoders, to sample the stochastic variable x from p phi x, a sample z is first sampled from some fixed distribution Q and then transformed using some function g phi z, as shown here. This reparameterization trick samples z from a normal distribution N and then transform it to a stochastic variable x, as shown here, which provides a continuous stochastic variable x to the function f theta, as shown here. Having the reparameterized p phi x, the objective L is expressed as expectation with respect to Q, as shown here. As a Q doesn't depend on phi, the gradient can be estimated with respect to phi in exactly the same way as a gradient with respect to theta, as shown here. We use Monte Carlo sampling to calculate this expectation. For more details, please check with these references. Thank you. Bye.